Today's lesson will be looking at section 7.4, determining chemical formulas. You can see the 4 objectives that we will cover in today's section. Number 1, define the term empirical formula. Number 2, be able to determine or calculate the empirical formula from either a percentage or mass composition of elements in a chemical. Number 3, look at the relationship between empirical and molecular formulas of a compound. And number 4, be able to determine a molecular formula from empirical formula data. A couple things as we go through and look at this section. Basically, empirical formula just means simplest formula. In a chemical formula, what we basically have is a whole number ratio of moles. So we've been doing mole calculations for quite a while. An empirical formula is just a whole number mole ratio. So again, as we said there, number 2, if we start out with a given amount of elements, whether it's percentages of elements or massive amounts of elements, we're going to be able to calculate the empirical formula for a chemical. Our starting points, as you can see here, the setup is very simple, very straightforward. We're either going to start with a percent composition of a chemical, or we're going to start with a mass composition of a chemical. Now, if we do start off with a percentage, we basically have to make one little adjustment here. If we have a percentage, we're just going to make the assumption that we have 100 grams of the chemical. That actually does not matter the amount of chemical. We're just going to use 100, so we have some simple numbers to work with. Given a percent, assume 100 grams, and basically our percentage changed to a gram amount, and now we're on our way with masses. As you can see, the next step is very simple. We take the mass of every element involved, and we calculate the moles for each element. Again, take the mass of everything, divide by its molar mass, and move on. I guess when we talk about what's new or what's different in terms of what we've done in the past, the next calculation is be able to take those mole amounts and just simply put them in a ratio. Okay. Take the actual moles. We have now a mole ratio. Our last step is tying really into what you've learned in math classes. You've dealt with ratios before in math class. All we're going to do now is take that ratio and make sure we represent it in whole numbers. So a final empirical formula is just taking the mole numbers that we calculated and converting them into a whole number ratio. Again, which you've done several times before in various math classes. All right, next, we're going to look at a sample problem on page 246 of the book. As you can see in the book there, they're talking about the analysis of a compound that has 32.38% of sodium, 22.65% sulfur, and 44.99% oxygen. And as you can see, what we talked about in our steps before, we're going to just make the assumption that we have 100 grams. Therefore, we can change these to percents, these percents to grams, and then take the percents and change them into moles, and moles into mole ratios. So as you can see there on page 246, you have 32.38 grams of sodium, 22.65 grams of sulfur, and 44.99 grams of oxygen. Dividing by their molar masses, we get mole ratios of 1.408 for sodium, 0.7063 for sulfur, and we get 2.812 for oxygen. Now, what we want to do is just put them in a ratio, as you can see in the book. That's not our actual formula, but hopefully that everybody can see 1.408 to 0.7063 to 2.812. From these numbers, you might be able to see the relationship 1.4 to 0.7 to 2.8 and realize we have a 2 to 1 to 4 ratio. Therefore, our final formula is Na2SO4. And again, you can see that followed through there on page 246. What I want to do next is on page 247, there's a sample problem here. Sorry, I'll back up one thing here. What if you didn't see that relationship? What if you weren't able to identify that it was a 2 to 1 to 4 relationship? One extra step that you have to do, and again, to kind of have it explained here, and hopefully that makes sense. If the mole quantities are not simple, meaning you're not able to easily see what that proportion is, what that ratio is, then you quite simply divide every mole amount by the smallest mole amount. So as you can see there, you have sodium, sulfur, and oxygen. You take each mole amount, divide it by the smallest. So for sodium, you would get 1.99 in the calculation. For sulfur, dividing it by itself, you get 1. And for oxygen, you get 3.98. So what we now have is a ratio of 1.99 to 1 to 3.98. Well, now we can take those numbers and see a better relationship that can get us an empirical formula that we need. 1.99 to 1 to 3.98. We now can round that and easily see that that's a 2 to 1 to 4 ratio. Again, do you have to divide this to show this work? No. A lot of times, though, it might be a little messy. You probably want to do this calculation to be able to figure that out. All right, on page 247 then, there's a practice problem number 1 involving iron and sulfur. And we want to be able to go through that calculation here. Tell us that we have a compound that has 63.52% iron and 36.48% sulfur, and we are trying to identify what the formula is for FES, the values of X and Y. So what I'm going to do here is I'm going to pause this and take a few minutes here, and after about 5 minutes, give you a chance to then kind of check your work and see that you get a right answer. So I'm going to pause it, and again, once you get to that point, you can then hit play when you're ready to continue. All right, so going through this calculation, again, our percents just changed to grams, and we should be able to be on our way. 63.52 grams of iron times 1 over its molar mass of 55.846 give us 1.137 moles of iron. We take 36.48% of sulfur, change it to mass, divide by its molar mass, 32.066. We get 1.138 moles of sulfur. So as we can see here, 1.137 to 1.138 is a 1-to-1 ratio. So our final formula is simply FES. One more quick example, page 247. They have a sample question involving phosphorus and oxygen, which you're able to work through. The thing there that they're showing is after they get from the mass of phosphorus and oxygen to moles of phosphorus and oxygen, you're going to see that you have 0.1431 moles of phosphorus. You have 0.3573 moles of oxygen. You divide by the smallest, and you're going to get 1 to 2.497, okay, phosphorus to oxygen. Well, our formula can't be 1 to 2.497, so here is where we sort of do a little rounding and make our assumption that we're going to call this 1 to 2.5. And in math class, again, we want a final answer that's a whole number ratio. So instead of calling it 1 to 2.5, we're going to multiply that by 2. And by multiplying that by 2, we're going to get a ratio of 2 to 5. So our final answer, P2O5, as they have written in that sample problem. All right, practice problem number 2 involves a potassium, chromium, and oxygen compound. So what I'm going to do is, again, pause it one more time, give yourself about 5 minutes maybe to work on this problem, and then when you're ready, you can hit play, and I'll go through the solution for that. Okay, from the question they give us percentages, so we can quickly do some mass measurements here. We have, from the percentages, will give us 26.56 grams of potassium, 35.41 grams of chromium, and subtracting those out from 100, we get 38.03 grams of oxygen. Multiplied by 1 over their molar mass, 39.08, molar mass of chromium, and molar mass of oxygen. In our calculations, we're going to get a couple numbers that are very similar. 0.679. Again, we've got actually 4 digits, so you can call it 6793, 0.6811, and 2.377 for our mole amounts. Again, once we have mole amounts, this does not become our subscripts, but what we do is we divide them out by the smallest. So when we divide the smallest by itself, we get 1. When we divide the 6.811 divide by the smallest, we get 1.002. We can call that 1. And then we take 2.377 divided by the smallest, and we get 3.499. So we get ratio of 1 to 1 to 3.499. We can call that 1 to 1 to 3.5. And then finally change it into a whole number ratio to get its formula, 2 to 2 to 7. So our final answer, K2 CR2 07. That concludes the short little clip on empirical formulas. The next clip tying into this would be how to determine molecular formulas, which is a very simple step in which we compare molar masses.